In this video, we're going to look at table of values, and we're going to analyze these tables. We're going to use the first difference, otherwise known as FD, and the second difference, SD, to determine, does this table of values represent a linear function, an exponential function, a quadratic function, or none of the above? If it is in fact a quadratic function, we're going to go a step further, and I'm going to show you how to use the table of values to actually write the function in standard form. So let's take a look at the first table of values here. Now, whenever you look at a table of values, the first thing you do is look at the progression of the x values. If these x input values do not progress by the same amount, you cannot go any further. And we're going to look at some examples where that happens, and I'm going to show you how to approach it. So here they go by +1, which is also notable because sometimes if they go, for example, by +2, +2, +2, you can progress to determine what type of function it is, but it's going to affect the way that you actually determine the actual quadratic function. So I can't emphasize this enough. The first step is to determine that the x value increases by the same amount, and also whether or not that same amount is by +1 each time. Okay, so this happens to meet both of those criteria. So now let's look at the first difference. The first difference is determined by taking the successive y inputs and subtracting the predecessor. So here, the key is to take 5 minus 3 so that your first difference, which I'm going to label it up here, the first difference for this table is 5 minus 3, which is +2. We're going to do the same thing here. We're going to do 7 minus 5. You always subtract upwards. 7 minus 5 is +2. 9 minus 7 is +2. 11 minus 9 is +2. It turns out that this first difference is consistent, and as a result, this is going to be a linear function. The linear function is going to have a slope of 2 because by definition, if the x value is advancing by 1, okay, the change in x is always 1 on this table, and the change in y is +2, that's the rise over the run with a slope equal to +2. So now having the slope of the linear equation, we would just plug any of the points in to get your b value and proceed to write the linear equation. In this next table, we see that the x values are progressing by the same amount, and that same amount is +1. If we look at our first difference, we see that if we subtract up, 6 minus 5 is +1. If we subtract up again, 8 minus 6 is going to be +2. And if we subtract again, 11 minus 8 is going to be +3. These are the first differences, and you can see that they are not the same. As a result, we know this is not a linear function. The next thing we do, folks, is we look at the second difference. Okay, we do the same thing with the second difference. We do this minus that, which is going to be +1. This minus that, which is going to be +1. And we see that the same difference is the same. It's consistent. That means this is going to be a quadratic function. Now, this table is what I call a perfect quadratic function, and here's why. First of all, the x values progress by 1. Okay, that makes a difference. Secondly, this table of values includes the y value that is associated with the input value of 0, otherwise known as the y-intercept. This is going to make our math easier. Both of those facts, the fact that not only does it progress by the same amount, but that set amount is +1, I'm talking about the x value, And the second important point is that it includes the y-intercept when x equals 0. Let me show you what I mean. Okay, the way we do this, folks, is we take the second difference, which we know is plus 1. We can only do this in a quadratic table that progresses of x values by 1. And we set the second difference equal to 2a. So here our second difference is positive 1 equals 2a. We solve for a, therefore a equals 1/2. Okay? Remember, the standard form of a quadratic equation is going to be y equals ax squared plus bx plus c. So we need to find these coefficients, the a, the b, and then the constant c. Okay, we already have our a value. Again, I want to emphasize, we cannot use this easy formula unless the x values are progressing by 1. Now, the fact that we have the y value associated with 0 is very helpful because we now know that our c value is 5. Look, if you look at the standard equation and you set x equal to 0, that's your y-intercept. So we've done that here in the table. They gave us the fact that the y value associated with x equals 0 is 5. So now we know our c value equals 5. The only thing we need to do now is find the b value. And the way we do that is we pick a point. So let's use the point 1, 6. We don't need our table of values anymore. Let's make some room. We don't need the same difference anymore. Once we have our a value, we have our c value, we do not need the table anymore. Okay, so here we go. We know that if we use the point 1, 6 from the table, we know that point is on the function. We're going to set 6 equal to our a value, which is going to be 1/2, x squared, which from this point is 1. So in other words, I'm plugging in 1 for x and 6 for y, plus b, which we don't know, times 1. Same thing, we're plugging in x equals 1, plus our c value, which we know to be 5. We're going to have 6 equals 1/2 plus b plus 5. We're going to move 5 to the opposite side of the equation. And we're going to get 1 equals 1/2 plus b. And when we solve for b, we get b equals 1/2. So now we have b equals 1/2. We have a equals 1/2. B equals 1/2. And c equals 5. So now we can write out our entire equation for this particular table. And we're going to get y equals 1/2 x squared plus 1/2 x plus 5. Here's our a value, here's our b value, and here's our c value. One more time. You cannot progress unless these x values are advancing by the same amount. If you're lucky, you're going to get two things. You're going to get the progression of the x values by 1, and you're going to get the y value associated with x equals 0. In this next example, we are told ahead of time that this is a quadratic function, and we're asked to find the equation using this table. So what do we notice? We always examine the table first, specifically the progression of the x values. We can see that the x values are marching along by positive 1. The next thing we look for is whether or not we see the y-intercept here, which is where x equals 0, and we do not see it. So let me show you how you can actually create the xy coordinates that precede the 1, 6 that you see here. First thing we want to do is find the first difference. And again, we know ahead of time that this is a quadratic function. So we're going to do 15 minus 6, which is going to give us a first difference of 9. And then we're going to do 28 minus 15, which gives us a first difference of 13 here. These are not the same. That means it is not linear, but we know that ahead of time. Next thing we're going to do is get the second difference. We're going to say 13 minus 9 is 4. Now, because we're told ahead of time that this is quadratic, we know that the second difference is going to be 4 throughout. So here's our game plan. We want to try to find this y value right here, okay? We know that the second difference is 4. So the first thing we want to do is find this first difference between the question mark and the 6 using this positive 4 as the same difference. We know the same difference is going to be positive 4. If the same difference is positive 4, which we know it is, that means 9 minus asterisk has to equal positive 4. That tells us that the asterisk has to equal 5. So we replace that asterisk with 5. 5 is the first difference between the question mark and 6. So we're going to say 6 minus question mark equals 5. Question mark has to be equal to 1. Now, why is this helpful? Because this is now our C value. So let's review what we did. We found the second difference. We knew, since we were told it was a quadratic, that that would stay consistent. We used that to find the first difference, and we used the first difference to find the y value at x equals 0. So what do we know? We know that because this progresses by positive 1, we are allowed to use the formula that the second difference, equals 2a. Here, the same difference is positive 4. That means we know that our a value equals 2. We also know that because we have the y-intercept, that our c is going to equal 1. All we need to do is find the b value. So we write our equation, y equals ax squared plus bx plus c. We already know that y is going to equal 2x squared. We do not know the b, plus 1. To find the b, we plug in a point, any point. Let's use 1, 6. We're going to have 6 equals 2 times 1 squared plus b times 1 plus 1. 6 is going to equal 2 plus b plus 1. B is going to equal 3. Therefore, our final equation for this table is going to be y equals 2x squared plus 3x plus 1. Again, very important. The fact that this progresses by plus 1 allows us to use that formula to get the a value. In this next example, we again first check to see that x is advancing by 1, so we can proceed with our analysis. Our first difference is going to be 4 minus 7, which is going to be negative 3. Here it's going to be negative 1. 5 minus 3 is positive 2. 55 minus 5 is positive 50. Moving to our second difference, we're going to do negative 1 minus negative 3, which is going to be negative 1 plus 3, or positive 2. Then we're going to do 2 minus negative 1, which is 2 plus 1, which is positive 3. So we immediately see that the same difference varies. So now we know this is not linear, and not quadratic. At this point, we evaluate as to whether or not this is exponential. If this is exponential, there's going to be a common ratio, meaning if you have 4 divided by 7, that should equal 3 divided by 4, which should equal 5 divided by 3, and we already see that there is no common ratio. Therefore, this table of values is none of the above. This next table of values is very interesting, and here's why. We check to see how the x values are advancing. We see that it's advancing +1 here, but +2 here. That means we cannot dive in to getting the first difference and the second difference. Continuing down, +2 here, +1 here, +1 here, +2 here, +1 here. Okay, so here would be one approach, folks. We can just work with a certain part of the table. So let's only work at this section where we're advancing by 1, 2 to 3, 3 to 4, and let's ignore everything else. If we did that, we would see that our first difference here is going to be 12 minus 10, which is +2. Then we're going to have 10 minus 12, which is -2. Then we're going to do a second difference, -2 minus +2, we're going to get -4. The problem with that, folks, is we don't have enough points to do anything with this. So that is just not going to work. Okay, how about if we ignore the advancements by 1 and just work where we see advancements by 2? Okay, so we're going to ignore this first one here. We're going to go 0 to 2, that's +2. We're going to ignore this one here. So now we have +2, +2, +2, and we're going to ignore this one. Okay, this should give us some information. However, let's write it in that this advancement is +2. The fact that that advancement is +2 means that if this turns out to be a quadratic equation, we cannot use that the same difference equals 2a. We are not allowed to use that unless the advancement is by +1. Okay, but we are allowed to proceed, and we can say that 10 minus -6 is the same as 10 plus 6, which gives us 16. 10 minus 10 is 0, and then we have -6 minus 10 is -16. The first difference is not the same, therefore this is not linear. Now let's look at the second difference. 0 minus 16 is -16. -16 minus 0 is -16. So this is indeed a quadratic function. The other thing that we notice is we do have the 0 point. So the only thing we can say at this point is that c equals -6. Now, how do we get the a values and the b values in this circumstance? Well, take a look at this original function, original table before we started doing all the erasures. And we're going to notice something about this table. You see this here where, let me just move some things around, sorry. Let's move this. Let's move this over here. And let's move this big table up. And what do we notice here? We notice that as we examine this original table of values, we see that this y value is the same for 2 and for 4. That tells me that our vertex is going to be in this area. In other words, if you have a parabola like so, and you have y values that are the same you know your vertex is going to be between there. So we have at x equals 2, y equals 10. At x equals 4, y equals 10. Parabolas are symmetric. Therefore, we know that the x value of the vertex is going to be at the midpoint between x equals 4 and x equals 2, which is none other than 3, 12. So if that's our vertex, how does that help us? Well, we know that negative b over 2a is going to equal the x value of the vertex. So we know that negative b over 2a equals 3. So we can use that as one of the three, we can use that in the systems of equations. Continuing with this problem, recall we have our c value because we have our y-intercept when x equals 0. We know that negative b over 2a equals 3. We determine that our vertex has to be at 3 because the y values are 10 and 10, which means our vertex is in between them in a symmetric fashion. 3 is the midpoint between 4 and 2. We set negative b over 2a equal to 3. We solve for b. We have b equals 6a. Now we can use this information along with any point to find our two coefficients plus our constant. We already have our constant. So let's pick an easy number. Let's choose x equals 2, y equals 10. So we're going to say 10 equals a times 2 squared. We don't know a as of yet. Plus b times 2 minus 6. Okay, we have our c value. That goes here. And the other thing we have is our b value. So we're going to plug in negative 6a for b. Now we're going to have one equation and one unknown. So we're going to have that 10 equals 4a minus 12a minus 6. We're going to have 16 equals negative 8a. Therefore, a has to equal negative 2. So if a equals negative 2 and b equals negative 6a, then we know that b is going to equal negative 2 times negative 6, or positive 12. We now, folks, have our a, b, and c values. And our final equation is going to be y equals negative 2x squared plus 12x minus 6. So what did we learn from this problem? We learned that if the x value does not advance by 1, we cannot use the first difference and second difference yet. We can isolate the portions of the table that advance by the same amount. We tried doing it, the portion of the table that advanced by 1, but we didn't get enough points to get the second difference. We then resorted to using that portion of the table that advanced by 2, and we found that the second difference was consistent and it was indeed a quadratic function. However, due to the fact that we used the portion of the table that advanced by 2, we were unable to use the shortcut that tells us that the second difference equals 2a. However, we saw within our table of values that our vertex was located in this position. We set negative b over 2a to the x value of the vertex, and we use that after solving for b in our system of equations. We picked a point, we plugged it in, and we got our 3 coefficients. Folks, keep in mind that once you know it's quadratic, you can always use a system of equations. 3 equations, 3 unknowns. But shortcuts like finding the vertex, and if the x values are advancing by 1, using that formula, which is that the same difference equals 2a, really make things easier.